Hello everybody, we are going to talk about the following problem. What is the minimal number of hyperplanes that are needed in order to dissect all edges of the hypercube graph in n dimensions? The hypercube graph has vertices which are the all 0, 1 vectors, and two vertices are connected if they differ only at a single coordinate. A hyperplane is the set defined using a single linear equation, and we say that a hyperplane dissects an edge if the two endpoints of the edge lie strictly on different sides of the hyperplane. What happens in dimension 2? How many lines do we need in order to dissect all edges of this square? So there are two possible configurations. We can have lines that are parallel to the axis, and we can also have lines that are parallel to one of the diagonals of this square. However, the following configuration is not allowed because it does not intersect the edges in their interior, only at vertices. What happens in 3 dimensions? How many planes do we need in order to dissect all 12 edges of this cube? So once again, we can have the same two configurations. We can have planes that are orthogonal to the axis, and we can also have planes that are parallel to a diagonal of this cube. In general, this shows that h of n is at most n. Now, if we play a little bit with this problem, it is not clear at all that h of n can be smaller than n. However, if we go to dimension 6, then there is a configuration of 5 hyperplanes that dissect all edges. Now, if you blow this example up to larger dimensions, we can see that always h of n is smaller than 5 over 6 times n. One application of this problem is to computing parity using threshold circuits. In this problem, we are given n input bits, and we would like to compute the XOR of these bits. The question is, how many gates do we need in order to implement this parity function? In this context, our gates are perceptrons, that is, they take several bits as input and output whether some linear combination of these bits are smaller than some threshold or smaller than this threshold. This computation is done in the real numbers. The reason this our problem is related to this problem of computing parity is that we claim that if we consider the linear equations on the first layer of this of a circuit computing parity, then it must dissect all edges of the hypercube. Why is that? If there would be some edge that is not dissected by any hyperplane, then this circuit would not distinguish between these 2 points because the first layer will evaluate the same for these 2 points. However, the parity function on these 2 adjacent points must be different. So this is a contradiction. This means that the size of the first layer of such a threshold circuit computing parity, at least h of n. The history of our problem dates back to the 70s, where O'Neill was interested in h of n. He showed that it is at least square root of n and at most n. Later, Alon and co-authors shows that if the equations defining the hyperplanes have coefficients which are only plus or minus 1, then at least n over 2 hyperplanes are needed, which is tight. And moreover, if the coefficients are known to be positive, then again, at least n hyperplanes are needed, and this is tight again. However, the problem in general remained open until only 50 years after the problem was raised. Better lower bound was shown. Yehuda and Yehudayov proved that h of n is at least n to the power 0.51. Also in a talk, they said that this exponent can be optimized. In this talk, we will talk about a lower bound, which is n to the power 2/3. Now, I want to propose a reason for why it was somewhat difficult to improve the lower bound of square root of n. First, how does the proof go for square root of n? So it turns out that each hyperplane cannot dissect more than a fraction of 1/square root of n of the edges. This is some anti-concentration bound, a Littlewood-Offord type bound, or Sperner theorem. In fact, once we get to square root of n hyperplanes, we can dissect almost all edges. To see this, arrange all points in the hypercube according to their Hamming weight. Now, if we consider these diagonal hyperplanes, then we can see that they dissect all edges in some layer. Now, if we use about square root of n middle layers, such square root of n hyperplanes, then we can dissect 0.99 of the edges. And this is unfortunate because we want to say that only n hyperplanes are sufficient, but even such a small number of hyperplanes can dissect almost all edges. The idea of Yehuda and Yehudayov to overcome this problem is to find a distribution over edges so that each hyperplane can dissect a smaller fraction of edges. This is strictly smaller than 1/square root of n. So because of the previous example, consider the following toy problem. Suppose that all hyperplanes are diagonal hyperplanes. Now, we want to find a distribution that evades all these hyperplanes. That is, a small set of hyperplanes cannot dissect a significant proportion of the edges according to this distribution. One possibility for such a distribution over edges is to start with a random Hamming weight that is uniformly distributed between 0 and n. And then, after we choose this random weight, we choose some random edge inside this weight. Now, because each hyperplane can dissect at most one such layer, then we will need at least n hyperplanes in order to capture this entire distribution, because it's uniformly distributed over different layers. Now let us have slightly more explicit analysis of this example. So define the normal vector v to be this normal vector to these hyperplanes. And the crucial observation in our final proof is that if we project a hyperplane on its normal vector v, then we get a single point. Moreover, if we project an edge in the cube on v, we get an interval. The claim is that the hyperplane dissects the edge if and only if the projected point and interval intersect. So in our example, suppose our random edge was between x and y, and x had uniform distribution of its Hamming weight. Now the projection of x on v ranges from 0 to square root of n. However, the length of an interval, that is the length of the edge projected on v, is only 1 over square root of n. Now, if we want our points or hyperplane to capture this edge or interval, we need at least n points. So this is a crucial fact in our proof. We wanted the projections of the intervals to be short, and also that the standard deviation of the location of the edge to be large, so that every set of points will not capture this edge. Our general proof follows the following framework. So suppose we are given m hyperplanes and we normalize the L2 norm of the normal vectors to be 1. We start with finding a point P in the solid cube that is far from all the hyperplanes. Then we round P to a proper vertex in the cube. And then we need to show that the probability of this random edge to cross any particular hyperplane is smaller than 1 over m. If we do that, we can use union bound to show that the probability that the edge will cross any hyperplane is smaller than 1. This is the framework of our proof, and actually this is also the framework of Yudai proof. What they do is to choose P using Banks lemma, which finds the point which is maximally far from all hyperplanes. However, using this deterministic definition of P will require some sophisticated round and bound methods. And now, if we use our view of using this projection, then we want P to have large variance on each direction that is parallel to one of the normal vectors v. We want P to have large component on each normal vector. So what we do is to define P using a probabilistic way. P is defined to be a large constant times a random combination of the normal vectors. Now, if we project our point P on any of the normal vectors, we get a large standard deviation of square root of n over m. And again, the length of the intervals that edges are projected to is only 1 over square root of n on average. So because hyperplane is a single point, the probability that this interval will contain the point that corresponds to this point is at most the length of the interval divided by the standard deviation of the location of the interval. And this tends to be square root of m divided by n. Now, if we substitute m to be n to the power 2/3, then we see that this probability of the edge and the interval to intersect is at most 1 over m, which is what we need. So beyond this problem that we discussed, that how many hyperplanes do we need to dissect all edges, there is also the problem of how many hyperplanes do we need to cover all vertices of the hypercube. So this problem is trivial, and we can cover everything using two hyperplanes. However, if we require each linear equation to use all coordinates, then we need at least n over 2 hyperplanes, and n are sufficient. However, recently it was shown that the answer is less than n, and this problem is still open. And another recent development is related to essential covers, which I'm not going to define precisely. And it is known that the number of hyperplanes is at least square root of n, and at most n over 2. And it was shown recently that a lower bound of n to the power 2/3. I think it is interesting because it gives the impression that maybe combining both approaches may be beneficial. Thank you. And this is the hypercube in 3 dimensions.